Ordered crystalline microporous materials such as zeolites and metal organic frameworks are used as adsorbents and as catalysts in separations and reaction technologies. Thin microporous layers of zeolites and morphs also used in membrane separations. In many cases, the intracrystalline diffusion of gas molecules has a strong influence on the separation performance of adsorbers and membrane units. And the objective of this presentation is to gain some insights into the diffusion characteristics of such materials. In particular, we consider the Maxwell Stefan description of mixture diffusion and highlight the importance of slowing down effects in a certain class of microporous materials. The background information on the Maxwell Stefan diffusion theory is available in these publications. Also, see my presentations, Uphill Diffusion and Diffusing Uphill, on my YouTube channel. Let us examine the IUPAC classification of pore sizes. A micropore has effective pore diameters smaller than 2 nanometers or 20 angstrom. A mesopore has pore dimensions in the range of 20 to 50 nanometers, and a macropore has pore sizes in excess of 50 nanometers. Let's examine the energy of interaction of gas molecules with the pore wall. This graph presents calculations using the Lennard-Jones 612 potential. For hydrogen, the potential energy of interaction is shown by the black lines. For argon, the interaction energies are shown in blue, and for methane, the interaction energies are drawn in red. R is the distance from the wall, and for each of these gas molecules, sigma is the size parameter and epsilon is the energy parameter. The sigma for hydrogen is smaller than the sigma for argon, and the sigma for argon is smaller than the sigma value for methane. Close to the wall, for smaller values of R, repulsion forces are dominant. Further away from the wall, attraction forces come into play, and the depth of the energy well is dictated by the epsilon or energy parameter, which is largest for methane and smallest for hydrogen, reflecting the stronger absorption of methane with respect to argon, and argon is stronger in its absorption strength than hydrogen. We note that at the distance of 1 nanometer from the pore wall, the potential energies of interaction are close to 0. Therefore, for mesopores with effective pore sizes larger than 2 nanometers, there is a central core region in which molecule-molecule collisions are dominant and molecule wall interactions are of negligible importance. Conversely, for micropores with pore sizes smaller than 2 nanometers, a gas molecule remains within the force field that is experienced with a pore wall. There is no central core region for micropores. Microporous materials can be employed in separation technologies that can be carried out in fixed bed adsorbers or in membrane constructs. In fixed bed adsorbers, the microporous materials are used in the form of pellets in columns in which the particles are packed. The separation performance is dictated by mixture adsorption equilibrium. In most instances, intracrystalline diffusion often, not always, leads to decrease in separation performances. In some cases, we can harness diffusional effects in order to reverse the hierarchy of adsorption strengths, and this is the example that is used for separating nitrogen from oxygen using LTA4A zeolite, or purifying natural gas by rejecting nitrogen. In a different kind of technology, the microporous materials form thin layers, typically smaller than about 50 micrometers, on a macroporous support, and separation is realized by permeating a feed mixture across the membrane. The permeation selectivity is a product of the diffusion selectivity and the adsorption selectivity. Intracrystalline diffusion is always important in membrane separations, and ideally the diffusion selectivity should enhance the adsorption selectivity. Let's see how a microporous membrane is constructed. Take the example of a ZIF-8. It consists of cages of 13 angstrom in diameter, and each cage is separated from adjacent cages by narrow 3.3 angstrom windows. These windows are flexible, and this flexibility allows molecules that are slightly larger than 3.3 angstrom to pass through these windows. Typically, the membrane would be constructed of thin layers of about 50 microns on a support, which is a macroporous. In this case, say a titanium support. And ZIF-8 is a good choice for separation of mixtures of, say, carbon dioxide, methane, carbon dioxide, hydrogen, methane, hydrogen. And the important advantage of ZIF-8 for CO2 methane separation is both adsorption and diffusion complement each other, leading to high permeation selectivities in favor of carbon dioxide. The company called NGK Insulators in Japan offer membrane modules which have a monolithic structure, and the inner walls of the tubes are coated with a thin layer, typically about 20 micrometers in size, this layer, and this layer consists of DDR zeolite that allows selective CO2 permeation from a CO2 methane mixture. In order to set up the formulation describing diffusion inside microporous materials, we draw inspiration from the works of James Clerk Maxwell and Maxwell Stefan for diffusion in ideal gas mixtures. Let's take the example of a mixture of three gases, a ternary gas mixture. In the Maxwell Stefan formulation, we assert that the force acting on each species is balanced by the friction that species experiences with partner species in the mixture. For example, the force acting per mole of species 1, that is quantified by the negative of the chemical potential gradient of 1, is balanced by the 1,2 friction and the 1,3 friction. The friction component 1 experiences with species 2 is proportional to the velocity difference of 1 with respect to 2. The friction component 1 experiences with component 3 is proportional to the velocity difference between 1 and 3. These frictional terms should be proportional to the amounts of partner species in the mixture. The 1,2 friction is proportional to the relative amounts of 1 and 2, and then therefore we introduce the mole fraction x2, and the friction between 1 and 3 should be proportional to the relative amounts of 1 and 3, and therefore we introduce the mole fraction x3 here. The constants of proportionality are the drag coefficients. In the Maxwell Stefan formulation, we define D12, D with a line through it, in this manner. This is and therefore the diffusivities have the physical significance of the inverse drag coefficients. R is the gas constant and T is the temperature. By introducing RT here, we ensure that the units of D12, D13, and D23 are square meters per second. Similarly, the force acting per mole of species 2 is balanced by friction 2 experiences in undergoing relative motion with respect to 1, and the friction component 2 experiences in undergoing a relative motion with respect to species 3. There are only two independent driving forces in view of the Gibbs-Duhem constraint shown by this equation. The term here d21 equals d12 because of the Onsager reciprocal relations, and therefore there are only three independent diffusivities describing ternary gas diffusion. Let us adapt the Maxwell Stefan formulation to describe diffusion of two gas molecules inside a microporous crystalline material. Example, let's have a look at the animation to show the diffusion of carbon dioxide and methane within the intersecting channels of MFI zeolite. In setting up the Maxwell Stefan equations, we use the same formulation as shown in the previous slide for a ternary gas mixture, and we identify component 3 as the pore wall. The pore walls may be considered to be stagnant. Another way of looking at it is to assert that the velocities of diffusion of components 1 and 2 are with respect to the pore wall. Following the Maxwell Stefan formulation, we assert that the force acting on species 1 being the guest molecule 1, with the which is the negative of the chemical potential gradient of species 1 at constant temperature and pressure, is balanced by the friction 1 experiences in undergoing relative motion with respect to species 2, and the friction component 1 experiences in undergoing relative motion with respect to the wall, which is species 3. Similarly, the force acting on species 2 is balanced by 2-1 friction and 2-3 friction. X1 and X2 are the mole fractions of the guest molecules in the adsorbed phase within the micropores. The mole fraction of component 3 is undefined, and therefore it is convenient to redefine this diffusivity D13 divided by X3 as the diffusivity of 1, which is the interaction that species 1 experiences with the pore wall. Similarly, we define D2 as the diffusivity that reflects the interactions species 2 experiences with the pore wall. Due to the Onsager reciprocal relations, D21 equals D12, and therefore for binary diffusion inside micropores, there are three diffusivities. D1 and D2 represent the guest wall interactions, and we have the diffusivity D12, whose physical significance has yet to be established. and we will establish its significance in the subsequent slides. From a practical point of view, we would like to know the component flux entering the microporous material, and the flux of component I, Ni, equals the framework density, rho, multiplied by the molar loading of the adsorbate inside the micropores, Qi, multiplied by the velocity, Ui, with respect to the pore wall. The units of the fluxes are moles per square meter per second. The Maxwell Stefan equations for binary gas diffusion inside micropores in the previous slide can be rewritten in terms of the molar diffusion fluxes N1 and N2 in this form. To recap, D1 and D2 are the diffusivities that reflect guest wall interactions. We shall now look at the physical significance of this coefficient D12, and we shall demonstrate that this diffusivity reflects how the mobility of guest molecule 1 correlates with the mobility of the guest molecule 2. In order to demonstrate this, let us consider CO2 hydrogen diffusion inside MFI zeolite that consists of intersecting channels that have dimensions of 5.5 angstrom. CO2 is a pencil-like molecule that has a much stronger adsorption strength than hydrogen that has a much smaller size. Let's look at animations created from MD simulations. The white spheres represent hydrogen molecules, and though they are highly mobile, their mobility is restricted in that it cannot travel long distances without encountering a stubborn, tardier CO2 molecule that does not allow it to pass by. In other words, the mobility of hydrogen is severely hindered due to the stronger adsorption and tardiness of the partner CO2 molecule. Correlation effects for CO2 hydrogen mixture diffusion in MFI zeolite considered in the previous slide may also be simply explained using the metaphor of a checkerboard in which the strongly adsorbed CO2 molecule occupy these adsorption sites within the MFI zeolite framework. A mobile hydrogen molecule here is able to traverse this area unhindered, but it cannot cross the contours drawn here, because in order to do that, the CO2 molecule has to vacate that adsorption site, and the vacation of adsorption sites by CO2 takes place very infrequently in comparison to the motion of hydrogen molecules. The net result is that the mobility or diffusivity of hydrogen is severely reduced due to the tardier CO2 molecule that is reluctant to vacate its position. It's akin to a game of musical chairs A hydrogen molecule can only occupy a chair if it's vacated by CO2. And this results in a slowing down effect for hydrogen. The mobility of the more mobile scooter is correlated with the mobility or lack thereof of this elephant. And correlation effects quantified by the D12 term in the Maxwell Stefan diffusion equations need to be duly accounted for in describing mixture diffusion in a variety of microporous crystalline materials. For quantification of the slowing down effects in mixture diffusion, we need data on the diffusivities D1, D2, and D12. We can use molecular dynamics to determine these diffusivities as explained in these publications, and the MD simulations for CO2 hydrogen mixtures are plotted against the pore occupancy in this diagram. The red circles represent the diffusivity of D1 of CO2. The cyan squares represents the Maxwell Stefan diffusivity of hydrogen in MFI zeolite, and the yellow diamonds represent the D12 term in the Maxwell Stefan equations. The open symbols indicated by these square symbols here represents the unary diffusivity of hydrogen, also from molecular dynamics, and the open circles represent the Maxwell Stefan diffusivity of CO2 in MFI zeolite, determined from unary MD simulations. The first thing to observe is that the Maxwell Stefan diffusivity of either component in the mixture is practically the same as the Maxwell Stefan diffusivity for unary diffusion. This is a persuasive advantage for use of the Maxwell Stefan formulation, because these diffusivities representing guest wall interactions in a mixture have the same magnitude as the unary diffusivities, provided they are compared at the same pore occupancy. This is explained in detail in the publications listed here. Let's have a look at the D12 term. At very low pore occupancies, the magnitude of the D12 term is significantly higher than D1 and D2. In other words, this implies that at very low occupancies, these two terms can be neglected in comparison with the terms that represent guest wall interactions. Put another way, the slowing down effects, which are quantified by these terms here, are of negligible importance at very low pore occupancies. However, as the pore occupancy increases, the magnitude of the D12 term is reduced to a significant extent And as pore saturation is reached, the D12 term is lower than the diffusivity of Maxwell Stefan diffusivity of hydrogen, but higher than the Maxwell Stefan diffusivity of CO2. From these equations, it implies that this term, which is the frictional contribution of D12, as it were, has a stronger influence on the mobility or flux of hydrogen, component 2, because it is the resistance is higher than the resistance offered by hydrogen on its own. So the slowing down effect has a greater influence on the mobility of hydrogen. So this term has a greater influence on the mobility of hydrogen than on the mobility of CO2, which is component 1. Let us examine this. The MD simulation data for the Maxwell Stefan diffusivities D1, D2, and D12 for CO2 hydrogen, shown on the previous slide, helps us to understand, rationalize, and quantify experimental data on CO2 hydrogen permeation across an MFI membrane. Now, CO2 has a much stronger absorption strength than hydrogen, but hydrogen has a much greater mobility than CO2. The permeation characteristics are dictated by a combination of mobility and absorption strength. Let's first consider the data on the unary permeation of hydrogen and CO2. The unary permeances are plotted here with open symbols. The diamonds are for hydrogen, unary permeance of hydrogen, and the circles represent the unary permeance of CO2. Due to the much stronger absorption strengths of CO2, the occupancy within the membrane are significantly higher than the occupancy of hydrogen. But you also note that the permeance decreases by about 1 order of magnitude with increasing occupancy in the upstream compartment of the membrane. So if we compare the data on the unary permeances of hydrogen and CO2, hydrogen has a much higher permeance than CO2. The story is completely different for the permeances in mixtures of CO2 and hydrogen. The mixture permeances are plotted by the fill symbols. The red circles represent the permeance of CO2, plotted as a function of occupancy in the upstream membrane compartment. And the yellow diamonds represent the permeance of hydrogen for mixture permeation, again plotted as a function of occupancy. There are two things to be noted. First, that the component permeance of CO2 in the mixture is only slightly lower than the component permeance of CO2 on its own. In other words, the reduction in the permeance in the mixture is negligible, almost negligible for CO2. On the other hand, the permeance of hydrogen for mixture permeation is about 1 to 2 orders of magnitude lower than the unary permeance. The reasons are twofold. Firstly, mixture adsorption is strongly in favor of CO2 and in disfavor of hydrogen, and that accounts for part of the lowering. But another contribution to the lowering in the permeance of hydrogen is the fact that hydrogen gets slowed down due to correlation effects that it experiences and explained in the previous slide. So a combination of mixture adsorption equilibrium and correlation effects accounts for the lowering in the hydrogen permeation in the mixture compared to the unary permeance. The Maxwell Stefan equations can also be applied to a binary mixture consisting of two species that are identical in all senses, except that one of them, say this one on the right called 1 star, is tagged. Tagged in experiments, it could be radioactively tagged. And if we consider diffusion in this binary mixture 1 and 1 star, the diffusivity one measures is normally called the self-diffusivity. The Maxwell Stefan equations allows you to interrelate the self-diffusivity with the Maxwell Stefan diffusivity. Due to the fact that in this binary mixture, the jumps of 1 and 1 star are correlated. In other words, if one vacates a site that will be subsequently occupied by 1 star, then the jumps from site to site are correlated, and such correlation effects leads to a lowering in the self-diffusivity as compared to the Maxwell Stefan diffusivity because of the self-correlation contribution, which in the Maxwell Stefan formulation is a kind of friction. If you look at MD simulations for unary diffusion for the Maxwell Stefan diffusivity for hydrogen, shown by these cyan squares, is the Maxwell Stefan diffusivity for carbon dioxide, shown by these red circles, and MD simulations for the self-diffusivity of hydrogen in MFI zeolite under the same conditions are shown by these squares, and the self-diffusivity for carbon dioxide are shown by these circles. We see in each case that the self-diffusivity is significantly lower than the Maxwell Stefan diffusivity due to correlation effects. Slowing down effects in mixture diffusion, so as illustrated in the foregoing slides for MFI zeolite, are of negligible importance for a certain class of zeolites that consist of cages separated by narrow 8-ring windows. Such zeolites are, for example, Shabbosite, DDR, and LTA zeolite. LTA stands for Linde type A. The correlations in all these zeolites are of negligible importance because the molecules jump one at a time across the narrow windows, and the intercage jumps are therefore not correlated. Let's see animations to illustrate that. The white spheres are hydrogen, and these pencil-like molecules are CO2. And you can see hydrogen undergoing intercage jump, but one at a time. Yeah, there you see it. The same is true for DDR zeolite. Again, the white spheres are hydrogen, and you can see hydrogen undergoing intercage hopping, one molecule at a time. These are animations for CO2 hydrogen diffusion in LTA zeolite. You can see the carbon dioxide is hovering around the window site, and hydrogen is undergoing intercage transport, one molecule at a time. So if you want to prevent or avoid slowing down effects, you should choose 8-ring zeolites such as chabazite, DDR, LTA, ERI as host materials. Let us examine MD data on diffusivities of CO2 and hydrogen in chabazite zeolite. As shown in the previous slide, these molecules jump one at a time across the narrow 8-ring windows, and the intercage jumps are uncorrelated. Consequently, the Maxwell Stefan diffusivity of either component is the same as the self-diffusivity due to the fact that the correlations are negligible. This graph shows the self-diffusivity of CO2 in MD simulations for pure CO2, shown by the open circles. The red circles show the self-diffusivity of CO2 in CO2 methane mixtures. The blue triangles show the CO2 self-diffusivity in carbon dioxide nitrogen mixtures. In ternary mixtures of CO2, methane and nitrogen, shown by the crosses. In ternary mixtures of CO2, nitrogen and hydrogen, shown by these stars. We note that if the self-diffusivity data compared at the same fractional occupancy within the pores of chabazite, the self-diffusivity of CO2 in the mixture has the same value as the unary self-diffusivity. This is an important and practical conclusion that is drawn from MD simulations. The same is true for the self-diffusivity of hydrogen. The open sim triangles are the unary self-diffusivities of hydrogen, and the self-diffusivity of hydrogen in a binary or a ternary mixture has the same magnitude as this unary self-diffusivity, provided the comparison is made at the same fractional occupancy. Data such as plotted here hold for other gas molecules and also for other 8-ring zeolites such as DDR, LTA, ERI, and further details can be found in this publication. This simplification for cage-type zeolites with 8-ring windows has important consequences for membrane permeation characteristics, as we shall discuss in the following slide. Following up from the previous slide on the MD data for self-diffusivities of CO2 and hydrogen in shavasite. Let's look at experimental data on the permeances of CO2 and hydrogen in SAPO34 membrane. SAPO34 has the same structural topology as shavasite zeolite. The component permeances are plotted against the occupancy in the upstream compartment of the membrane. We note that the component permeances of CO2 in any mixture, be it carbon dioxide methane, carbon dioxide nitrogen, carbon dioxide hydrogen, or a ternary mixture of carbon dioxide, methane, and nitrogen, the component permeances are the same in the mixture as the unary permeances. The same is true for hydrogen. This is the data. The open symbols represent the unary permeance of hydrogen, and the blue triangles show the unary permeance, the permeance of hydrogen in mixtures with nitrogen. The green squares represent the permeance of hydrogen in mixtures with methane. The yellow diamonds show the permeance of hydrogen in mixtures with CO2. Compared at the same value of the occupancy in the upstream phase of the membrane, the component permeances of hydrogen are the same. This is an important and practical conclusion that also holds for nitrogen permeance, for methane permeance. The detailed explanations and modeling information is provided in this publication. Also see my presentation on the spreading pressure concept in membrane permeation on my YouTube channel.